Sweet. All right, can everybody hear me? Hopefully that works. All right. All right, well, hi everybody. And again, thanks to the organizers for such a nice conference. As you can probably hear, despite representing Google, I'm actually a native son. I started here, I went to UNSW for my undergrad, worked on spin qubits, but then traded them in for something a little easier to fabricate. And also, as you might have guessed from that, I'm an experimentalist rather than a theorist, so it's always fun to be the first talk at a theory conference this way. So hopefully this will be a sort of easy introduction. There'll be no test at the end. But yeah, I'm here to kind of represent a lot of work done by Google in the last year on a bunch of different projects, so it'll be a little bit of a greatest hits. Feel free to jump in with questions during or afterwards. You can come and find me if you really want to grill me. But I thought I'd start with sort of why are we all here, which is QEC is functionally a necessary ingredient for us. We want to build a quantum computer. We're going to need it to be very good. So the kind of gate errors we're looking for in practice are going to need to be something like 10 to the minus 10. Now over here I have very ambitiously, I wonder if this has a dot, it does, represented the world's best physical qubits at something like 10 to the minus 4. Experimentalists might already get mad at me for that. But you might notice there's a big gap between what I said we wanted to be and where we are. Theoretically, it might be possible to just build extremely good physical qubits, but at least at Google, we have a different option, which is we're going to add QEC, make logical qubits, and then after that, victory boils down to one thing, which is scaling, making a lot of them. So this feels like a kind of good setup. You might notice I've labeled two important things here. One of them is less important to me, at least, which is break even, which is just paying off the cost of doing the QEC in the first place. Then the second thing I've kind of labeled victory, which is being able to really push the error rates down to stupendously low levels that will actually let us do something practical with the quantum computer. Now, what makes me think that that's possible? Broadly, the real promise of the error correction is this empirical relationship, let's say, that we can kind of get exponentially better by scaling. So a relatively, well, maybe modest is the wrong word, but by increasing the number of qubits a little bit, we can get the error rate to go down a lot. And that boils down to needing your physical error rates to be below some threshold rather than actually improving them all the way to 10 to the minus 10. Once you've got this characteristic, which we measure, or at least we often talk about in this parameter called lambda, if lambda is big, the QEC gets better as the distance goes up. And then you've satisfied this requirement. After that, all we have to do as experimentalists and engineers is make the thing big instead of make it any better. So that's essentially the kind of big challenge. Now, because I work for a company, I'm sort of required to show you this. But just to really convince you that that thing I just said is a thing we're taking seriously, we plan on making the thing better. And then after that, we plan on making it truly massive, like stupendous numbers of qubits, millions, tens of millions. This is an engineering effort of a very different flavor than if I tried to invent new physics to produce a 10 to the minus 10 qubit by itself. But this is the plan that we're taking pretty seriously. And how exactly we're planning on doing it, at least up till now, is using this one cool trick, the surface code logical qubit. So this is one of many, as I'm sure you're aware, QEC codes, but it's very close to my heart as an experimentalist because it's very nice to me. It requires d squared physical qubits for the data qubits, and other than that, it only requires a 2D local connectivity, which is, the same shape that chips are. So that makes it much easier to build. Now, what exactly do I have to do? I'm going to skip over this quite quickly because I'm sure you've all seen the surface code circuits before. But broadly speaking, in the code, we use local entangling gates, 4 layers of them. We have measure qubits and data qubits. The measure qubits do operations to check the parity of a local set of data qubits. And the data qubits have their parities checked by the surrounding measure qubits. You can see that this produces a sort of fun interlaced pattern of 4 layers of 2-qubit gates, which to me are the really hard bits. There are some single qubit gates floating around in red. And then there's this thing at the end, the measure and reset layer, and we do some dynamical decoupling, some kind of error protection on the data qubits at the same time. So the kind of biggest experimental challenge is pulling off these 4 layers of CZ gates. The other biggest experimental challenge is just hidden inside this one box. This diagram is absolutely not to scale. The M and R operations are the most difficult. They take about 70% of the cycle duration. So in our structure, this looks pretty, but this box actually hides a lot of the nasty details that I'll be bringing up again later. OK, so originally I promised that we were going to scale all the way to the 10 to the minus 10. Before we do that, we're just going to scale a little bit. So the kind of key idea here is the code should get better as it gets bigger. So this is the smallest surface code that we like bothering with. It's a distance 3 code, so it can only really correct one thing going wrong at a time, basically. But it only takes 17 qubits. The next size up that's sort of sensible is a distance 5 code. It can correct sort of 2 errors at a time, but it takes more qubits, 49 in this case. So the key result we're looking for here is that the big one does better than the small one. What is standing in our way? Qubits are standing in our way. Every time you add more qubits, things get noticeably harder. What exactly do I mean by that? Things like, when you've got 50 qubits instead of 17, the calibration overheads are quite a bit more difficult. You've got a lot more work to do to learn how each qubit wants to be operated. Also, each of the qubits have a bad habit of talking to each other, even over quite long distances in a practical device. They also induce correlated errors over long distances, and you've got to do more work kind of multiplicatively as you add more qubits to deal with those kinds of problems and try and calibrate them out. Of course, the device is physically bigger, so the fabrication gets more difficult, the fabrication cost goes up, packaging the thing in order to put it into a fridge and wire it up gets harder. And then the last kind of most pernicious thing is rare failures become common. When you're making a small device, you can make kind of 10 or 20 of them, and if 1 out of 10 of them has a fundamental dead object on it, you're not that worried, most of them work. As they get bigger, those rare failures tend to become a lot more common, and then you rapidly can't post-select out fabrication problems, you rapidly can't post-select out calibration problems. So this is perhaps the most dangerous thing as you make the device bigger. You're losing one of your best techniques to make sure the device is good. So to flash back now into the distant past of 2023, this is a plot from one of our big papers which shows you we got a really nice device, we got it in the fridge, and we started down here. What this plot is the goodness of the distance 5 one versus the goodness of the distance 3 one. So down here means the distance 3 is performing better than the distance 5, which, as you remember, is what I promised wouldn't happen. So we had to fix that. So what do we do? Here we kind of gleefully labeled system improvements, but I'm going to tell you a little bit more about what that means. This was kind of months of work of large amounts of our team working on improving the individual gate fidelities via calibration, improving how those gates worked together in context of the QEC experiment, developing new, even physics tools to suppress issues on chip, like the crosstalk and correlated issues I was mentioning before. We have a specifically pernicious error in superconducting qubits that you can come and ask me about if you really want to know, because I will rant, called TLSs. And learning where they live in frequency space and having the qubits avoid interacting with them is like one of our key techniques. And then also improving the kind of a really soft side of QEC, improving our decoding through improving priors, learning more about the device, and then also actually improving the way we're algorithmically decoding. And all of these produce this trajectory that over time the performance of both of them improved, but the performance of the distance 5 code improved faster until it was actually better than the distance 3 code. So that's pretty cool. That is what I promised would happen. The bigger code is better. But like not really. So this is also a plot from that paper, where this is, I would say, the skeleton in the closet, although it wasn't so much in the closet because we published it. But what we really promised you was a descending line here, that the logical error rate per cycle goes down as the distance gets bigger. And you might notice this 1 is an error scaling factor, so 1 is the actual experiment we ran, and that green one doesn't keep going down, it flattens out. And so that is not what I promised you. We can't actually handle that. Hitting a lambda of 1, like having the distance 5 perform the same as the distance 3, is not enough to keep scaling. Here is like a sort of less well-presented but more numerically detailed estimate of the same kind of thing. And what you'll notice is these curves are different noise rates, and here labeled are all of the different lambdas involved. You can basically see that just because it's descending at the start doesn't mean it's still descending at the end of each of these curves. And so specifically, you can get quite a good lambda at the start, the difference between the first 2 points, but still have a flattening out code that does not actually have a scaling lambda, and therefore if you keep making it bigger and bigger, it stops improving. This is a bit of eyeballing rather than really good analysis, but you can kind of see here that if I have a lambda of 1.3 at the small distance codes, it stops descending entirely. So 1.3 in 3 and 5 is not actually below threshold. You do not actually get to scale to success. At sort of 1.5 at the start, it sort of bends a little bit, but at least it's still descending. So 1.5 is kind of like a better place to really aim for. And actually, it's by about lambda of 2 at the start that you see the line actually really straightens out. So this curving at the top is really a small size effect. When you're near threshold and you're only looking at small codes, you should not trust the scaling that you see. But I started this talk by saying that this was about getting below threshold. So what does that really look like? It might not surprise you to learn that I did not make this slide. A graphic designer did. But broadly, we've been working on the old Sycamore architecture for several years now, and we finally have enough improvements that we've decided to pick a new tree, also California native. But basically, what are the differences here? We've done a lot of work hidden inside that nice box, and I'm going to tell you the two most important things we did. One is that it's bigger. So this lets us fit a distance 7, which means theoretically-ish 3 errors at a time, and that is more than 2, so that's nice. This meant that we had to get around a lot of the problems I was mentioning before, like making the fabrication yield successfully, packaging and wiring the thing became a lot more difficult. But the other thing is the physical device itself got a lot better. So this was very exciting for the people using the device. So here is the distributions of different errors. So like each one of these little steps, this is a cumulative histogram of the 1-qubit error back on the old devices, the Sycamore device. And this is the bigger device. And you can see, so this is from our previous paper, 23. You can see that all of these distributions have improved. They've kind of moved over. And that's really good for us. Most of these are actually attributable to a substantial improvement in the T1. So like, I feel like for a very long time, Google was sort of renowned for having these really big, very controllable devices with very bad T1s. And to some extent, we've now actually managed to sort of get the best of both worlds. The device is, if anything, just as controllable or more than our previous ones, but this is a massive improvement in T1, and that really underlies not just the improvements in the error rates, but I can freely tell you it's a lot easier to use and calibrate the device when you've got more T1. And maybe the biggest expression of that is our bulk detection fraction, which is when you're running QEC, like how many local error detection events do you discover are basically halved, which means that not only does the device behave better, but also the decoder has a lot less work to do. And basically, due to those two things, we're now in a situation where instead of having to tell you about the skeletons in the closet, I get to just say there's a clear exponential scaling. So here is over the course of a logical error correction experiment, a memory experiment, and here's the logical error rate. But after doing these fits, we extrapolate to what it is versus distance. And you can see there's like a really nice straight line with 3 points on it instead of 2. And the lambda is now like 2.4, which is well beyond that regime where I don't have to really worry about the small size effects anymore. Remember, it like continues descending at like 1.5, so that's one number to keep in mind. But after about 2, you're pretty much straight lines, provided you keep the same error rates as you get bigger. So that's very exciting for us. The other thing that is on this plot, which I feel I should point out, like I said, this is not my favorite metric, but it's here, that we've also exceeded the goodness of our best physical qubits. So we have, in some sense, paid off all of the work we did to generate the massive device and do all of these extra operations. We have finally kind of beaten just one transmon by itself. Cool. So I could, broadly speaking, end my talk here. When the QEC gets bigger, it gets better, and also when the device gets better, it gets better. So that's very nice. It won't surprise you to learn that there are many things that are still worth talking about when you operate one of these experiments. And just getting below threshold is like a nice headline result, but actually there's a lot of cool stuff to talk about. And so here are some of the load-bearing details in our work. And these are going to keep coming up again and again. And when you read our papers in the future or anyone else's, these are really good things to look for, because these are kind of where all the really difficult bits turn up. First is sort of doing the right experiment at all. So I mentioned this kind of very briefly earlier. But the experiment we're doing is a memory experiment, which is not all of quantum error correction, and it is not logical computation. So we are sticking to the kind of first step along that to start with. But what a memory experiment boils down to is just, can you get a logical qubit to be given a state and then keep it instead of dropping it on the floor? This involves many kind of moving parts. First, you've got to be able to initialize a logical state in the surface code. For X and Z states, that's very easy, so they're the ones we're looking at. I will mention here that for other states, Y states, and for arbitrary states, it's much more complicated, and I'll show you some interesting things about that later. But for now, sticking to the easy fault-tolerant states. After that, we've got to hold on to it for many rounds of error correction, where a round was that thing I mentioned before, where you've got kind of 4 layers of 2-qubit gates. You get out a bunch of measurement results, And you've got to put all of those measurement results together in order to, at the end, when you measure out all of the qubits, work out what the logical state was and whether or not you should correct it. And once you've done that, you can see how good your qubit was. Like basically, if I prepared it in a state and then I did the error correction, did I end up at the same state at the end? And that's actually the numbers for logical error rate that I've been showing you this whole time. Now, it's very important when you run such an experiment that you avoid cheating. There are many, many ways to cheat. Here are 4 of my favorites. First, you have to run a lot of the small distance code patches to avoid villains. I'll show you more about what I mean in a second. You also have to make sure you run the whole experiment for a really long time so that you're not confused by short time effect. You have to make sure you run a lot of these experiments over many hours so that you don't just like get your device up to kind of a heroic level of performance that degrades after 10 minutes. This is not really, convenient for future computation. And maybe most importantly, you really have to not post-select. So anything that happens, even if it's not supposed to happen in your device while you're running this experiment, you kind of have to cop it. So I'll go into those in more detail. First, you really have to run a lot of small codes. Imagine I have a device and everything's amazing except one gate is really bad. If I dump a distance 3 patch on top of that one bad gate, it is not going to work. It can only really handle one error. If that keeps happening every round, the code is going to fail. On the other hand, a distance 7 code can handle this. It'll handle it with about the performance of a distance 5 code, but it'll handle it. And so if the 3 totally doesn't work and the 7 does, this produces a great lambda, and then I can go and claim that I'm way below threshold. So in order to avoid doing that, you have to make sure you run enough D3s that anything bad on the device is included in the D3 performance. And that means you have to run it kind of, here I've shown, we've tiled these little D3 codes all over the device so that any bad thing is at least impacting the D3 numbers. You could do the same thing at D5, and then of course in this device we can only fit one D7. So this is one way of cheating you have to avoid. Another one I mentioned is you really need to prove that once you've hit a good bit of performance, you have to be able to stay there. So this is the same error correction experiment running, I think it was every few minutes for 15 hours. And so we've, oh no, sorry, this one's less dense than that. This is on the hour, maybe. I'll look it up. But the point is you can see that it's a relatively nice flat line. It's not like we have one of these characteristic things where we've really calibrated a very unstable high performance point and then drifted away from it. This is a very stable high performance point. And finding these is a calibration challenge, but they exist and you can land yourself right in the middle of one of them. And this has like pretty minimal recalibration along the way. This is really aided by this thing we call TLS forecasting. You have to know where your like primary errors are over time and what things can drift in that would cause your error to skyrocket. And then you really have to avoid them in advance in order to produce this kind of performance over such a long time scale. Sweet. So another good caveat. Oh, yeah.
I'm intrigued by the forecasting aspect of the TLS forecasting. So you're saying you're not just detecting them where they are, but like predicting their leading?
Yes. So I don't have a plot for this, but TLSs have a myriad of interesting behaviors, but they're relatively predictable. So the 2 kind of most classic behaviors that you can see even in like old Paul Klimov papers are big TLSs either tend to wander around but not go that far from a sort of center point, or they tend to have quite a big jump but really have telegraph noise. So they like sitting at 2 different locations in frequency space. So in the drifty case, you just have to give them a wide berth. In a telegraph case, you have to learn exactly where they like living and then avoid both of those places. So this is the kind of tricks. There are kind of other things that sort of look like TLSs that aren't, that we also do forecasting for to avoid. And sometimes, like for this one, we were really avoiding everything, but if you're trying to run a fast experiment, maybe you can work out where the telegraph TLS is and then maybe not avoid its second location, but you're kind of asking for trouble in the long run. But yeah, this is kind of what we mean by TLS forecasting. There are things in our device that change over the sort of hours time scale, but if you look at the device for days, you can kind of work all of those things out and then avoid running into any of them. Sweet. So another big caveat that you should always ask a superconducting person about if they ever show you an experiment is what did you do about the leakage? I have been saying the word qubit a lot. I do not have qubits. Transmons have a lot of energy levels, and I only like the bottom 2. The next energy levels up tend to have much worse coherence times. They don't work for any of our gates. So if we populate these higher levels, we are in for trouble. And specifically what I mean by trouble is this kind of thing. If one of the qubits leaks, broadly it stays leaked for a really long time. It's on the same time scale as T1, although it is shorter. when it hits a gate operation, because we calibrate the operations expecting the computational state, usually something bad happens. And in particularly pernicious cases, like most of our 2-qubit gates, what it tends to do is leak the other qubit involved. That qubit then goes and crashes immediately into another gate, which leaks another qubit. When it hits measurements, the measurement just does not work correctly at all. It gives you somewhere between a random number if you've calibrated without it, or the measurement can tell you the qubit is leaked, but either way, you are not learning the error correction information you want to know. And this lasts for a very long time, producing Pauli errors along the way. So this is not what error correction is designed for, and it's not very good at handling it. You might notice here that the leakage sort of disappears when it hits one of these reset operations. That's because right after measurement, I can pretty much dump out the entire state of the qubit. So that is a very convenient place to remove leakage. But what do we do about these really long purple bars on the data qubits? So one of the really load-bearing details in this experiment is we spent a lot of time working on this data qubit leakage removal, which is a non-Clifford, like really physics-level operation that we're doing. What this looks like is actually about half of how we do our CZ gate. What's it really doing is exchanging the 0-2 state of the 2-qubit manifold into the 1-1 state. And what that does is, because we have this reset gate and we've prepared this qubit in a really good 0 state, it basically guarantees that if this qubit's in 1, nothing happens. But if this qubit's in 2, the 2 state gets sort of split up into 2 photons, and one of them ends up on this measure qubit, where again, we can just reset it out. So this turns out to be a really, really effective way of sucking the leakage out. It leaves behind an excitation that you might not have had before. So it kind of turns a leakage error into a Pauli error, but Pauli errors are the thing that error correction is good at, so this turns out to be an extremely effective maneuver. I mentioned before, it relies on having very good reset gates, and now you're using it twice, so you should really be enthusiastic about this operation now if you're going to go for this strategy. But in terms of the actual experiment itself, using this operation instead of not using it results in a substantial improvement in the error scaling. So like a 35% increase in the actual lambda we see. You can see that basically it only makes the distance 3 code a little bit bigger because the distance 3 code is small, so the leakage actually doesn't have that far to spread. But as the code gets bigger, the leakage becomes a worse and worse problem, so removing it becomes more and more important. So for the distance 5 code, it makes a substantial difference. We didn't in the paper run this experiment on the distance 7 code, but we have since, and I can tell you the difference is even bigger. So we expect that to basically continue as you make the devices bigger and bigger. As the distance gets bigger, it's even more important to handle kind of viral correlated errors. Sweet. And then one last thing is in order to be able to do computing in the end, we need our decoding to happen while we run the computer. We're not doing sort of magic state teleportation injection yet, but one day we will need to. And so here for this experiment, we also ran our decoder in real time. That is not the one that produces the headline number, but it does achieve a lambda also beyond kind of 1.5, so it's in the sort of scaling regime. You can see we ran our real-time decoder, and here I'm showing you the latency, which to me is the kind of best figure of merit for whether or not your real-time decoder is operating correctly, which is that the latency has to be a number you like, and it has to not really get worse as the code runs. So here you can see we ran for 1 million cycles, which is a very long QEC experiment. And the latency stayed relatively stable. It's sort of around this 60, 70-ish microsecond regime. That is pretty good, but it's not as good as we would like. So keep in mind that this number, especially if it's this size, is going to be one of the limiting factors in clocking the final quantum computer. But the fact that it is a number and we measured it and we have a system that does this is sort of a nice achievement. So that's one less skeleton in the closet. We do have a long way to go with real-time decoders, though, because our best decoder actually was not a real-time decoder. It won't surprise you to learn, me working at a software company, a neural network decoder based on a transformer architecture. And that's actually what achieved the best lambdas and the best error rates. So you can get a 15% increase in lambda by throwing a lot of compute at it. But there's nothing fundamental going on in this bucket that can't be done in the real-time bucket. So we know we have a long way to improve real-time decoders, not just to do things like bring this latency down and make the computer faster in the end, but also improve the accuracy. Because basically every time lambda goes up, I have to make fewer qubits, and that does make me happy. And so for one last caveat, maybe the one that is most important and that you should definitely ask people questions about, is this thing, which I'm going to call the impact flaw. I'll tell you more about what it actually is, but this is also a flashback to our 2023 paper. Where here actually we're running a repetition code. So like the surface code numbers are up there. These two little black dots, you can see if you squint, maybe you think it's a line that's going down. But these blue dots are running a one-dimensional code instead of a two-dimensional code. So it's a classical code. It's not real quantum error correction, but it's the same operations for the quantum computer. So if you're good at this, you're probably good at the surface code. It's just harder. But also, because the repetition code is so much easier in terms of the threshold, you get to see this sub-threshold scaling performance over many orders of magnitude before you can achieve the same thing for the surface code. So that's really cool. You can see we do get this really nice straight line, except that we crash into something, which is very unfortunate. So around 10 to the minus 6, the performance of this classical code stopped improving, which is bad. Now here I've kind of given the game away by saying that the straight line performance comes back if we remove this high energy event. So what do I mean by high energy event? So this is a plot from a different paper where we were looking specifically at these events. What's going on here is a color map. Dark colors mean qubit working. Bright colors mean qubit not working. This is a really, really long time period. This is in milliseconds, whereas QEC cycles are like microseconds, so this is like a stupendously long time scale for our device. And as you can see, something happened about there, and a humongous chunk of my device completely stopped working. It might not surprise you to learn that that is not a thing that quantum error correction is good at handling. So what exactly is going on in the physics? Broadly speaking, what we're blaming here is nuclear physics. Every now and again, very rarely, but every now and again, a gamma ray or a muon, some kind of high energy radiation particle, comes and interacts weakly with our substrate. But a weak interaction in nuclear physics is a very, very strong interaction in cold condensed matter physics. So what this tends to do is dump loads of really high energy phonons. Now, I've mentioned before, we work on superconducting qubits, and so it's important that they remain superconducting. These high energy phonons have a bad habit of preventing that, and the actual way we represent that is with these things called quasiparticles. If anyone in superconducting physics says the word quasiparticle to you, you can ignore that and just think non-superconducting thing. And non-superconducting thing is bad because superconductors don't have loss. Non-superconducting thing does. So when the quasiparticle comes and crashes into the Josephson junction, which is the key element in the middle of our qubit that provides the nonlinearity that lets us make it an actual qubit, what it tends to do is suck the energy straight out of the qubit. It's a dissipative object, so just like an electron in a resistor, it tends to dump that energy back into low energy phonons, and I can't get it back. So that makes the T1 totally disappear, let's say. Usually the T1 is in tens or hundreds of microseconds. During one of these bursts where there are loads of quasiparticles, we hit T1s of less than a microsecond, which is the length of the cycle for QEC. So the qubit basically is a dead object during one of these events. Oh yeah, so here is like even more details about that thing I just said. Basically, once you have quasiparticles sitting next to the junction, this is the problematic matrix element, basically. This is the transition we really don't like. The quasiparticle can hop from one side of the Josephson junction to the other, gaining the qubit energy, which it then dumps out into a place I can't retrieve it. This process is unfortunately like pretty strongly coupled. Like you can't really avoid this happening. If there are quasiparticles around, which there should not be, the qubit is not going to be very good. But the quasiparticles generated by these events only disappear over milliseconds. So once this happens, my qubit is very bad. Now the other thing you'll notice here is that I've labeled two energy levels, and these are the superconducting gaps. So in a superconductor, these are sort of like the lowest level available energy states for the quasiparticles. And this is the energy space in which the quasiparticle is gaining the qubit energy. Now the reason there are two of these gaps is because, like in most superconductors, aluminum's superconducting gap depends on the thickness and many of the other kind of geometric details. We naturally make our qubits sort of looking like this. We put down a thin layer first, and then we dump a thick layer on top of it. And the thick layer needs to be thicker because I need to be able to deal with these steps. But yeah, so what that naturally means is there are two superconducting gaps in the problem. They don't tend to be that far apart because we don't tend to pay a lot of attention to this, except recently we discovered it's a good idea to. So this gap difference is about 3 gigahertz, and the energy of the qubit is about 5. So that's how this diagram basically looks. But that was optional. I mentioned that the superconducting gap depends on things like the thickness. And if you use a much thinner layer as your thin layer, the gap actually goes up very quickly. So once you have a very high gap, you can actually totally prevent this transition that sucks in the qubit energy. Basically now, in order for the quasiparticle to tunnel from one side of the junction to the other, it needs to find something like 10 or 12 gigahertz worth of energy, and the qubit just doesn't have enough energy to produce that. So this transition is no longer possible, and actually this means that even if you have huge numbers of quasiparticles in your qubit, it can't actually suck the energy out anymore, and you've removed its primary way of killing the device. And so what that looks like here in a device we've made with 12 qubits, and half of them are gap engineered and half of them aren't. Gap engineering is this thing where I make the thin layer very, very thin and have a really big gap difference to prevent this transition. And what you can see here is we've found one of these high energy events where a gamma ray has struck the device, and you can really tell which qubits are sensitive to the process and which ones aren't. So this is a really fun experiment, but this was a very simple device. It was 12 qubits, uncoupled, no error correction. So another kind of major thing to do is then integrate it into our big Willow, and Willow does have full gap engineering protection on all its qubits. And what this means is that when we run another one of these repetition codes, instead of stopping at this floor at 1e6, we can blast straight past it, which is really, really cool. Except that we stop. So all the way down here at 10 to the minus 10, we actually see another leveling off. What this means is we've still got a big correlated problem. It looks very kind of similar, although a little bit different. And if you want to know more about that, come talk to me. So now instead of finding one of these events every about 10 seconds on our biggest device, we're now finding one of these kind of bigger, different events, but about every hour. So I mentioned before that one of the biggest culprits is these like gamma rays hitting our device. They tend to hit, of all of the hits we found when we were seeing one every 10 seconds, like 97 to 99% of them were gamma rays. They come from nuclear decays in the metal building the fridge, in the concrete of the building, and they're kind of really hard to get rid of. But one per every couple of hours is actually the right rate for high-energy muons from space. And these things have a lot more energy, they're harder to avoid, they're virtually impossible to shield without going underground. And they dump enough energy that their errors are, at least theoretically, kind of masked, but not completely removed by the gap engineering. So we've sort of removed one problem, but we have a kind of more pernicious version of the same thing. We're like investigating this very actively, as you might imagine. And hopefully I'll have more to say by the March meeting. But also, this is not the only weird error source we find in the device. So this is across the qubit indexes. So this is the repetition code sort of in one dimension. And this is what one of those error bursts look like. It's like a large fraction of the qubits kind of not working very good for quite some time. But we also see these kinds of events. And this is even with the TLS forecasting. There are some like extremely rare transient errors that make one of the qubits sort of not work, again, for like quite some time, millisecond scale. Some of these rare things are attributable to just kind of failures of TLS forecasting, like there's a TLS with a very, very low rate of movement. So even though we look at the device for days, we don't find this one and forecast it out. And then we run the experiment and we just get unlucky and it flips off during. But there are also other sources of this that we're not really sure we understand the physical mechanism for yet either. Now, why would these kinds of things be a problem? Well, it's fairly obvious why this would be a problem. You're removing a large chunk of your distance in the error correction code. This one may be less pernicious. You might say to yourself, oh, well, I mean, you're only killing one qubit. It's a big code. Maybe that's fine. But like I mentioned at the start, doing the right experiment is very important. We've only done kind of the very first experiment. And in general, in the kind of error correction that we're looking at, where we plan on doing things like lattice surgery, and the stability experiment maybe being the kind of key metrology experiment for this maneuver, it is actually important that we don't have errors traveling easily in the time direction in some places in our computation as well. And this kind of thing would make it very easy for an error chain to travel a long distance, like a really long distance in the time direction. Again, this is milliseconds, so it's 1,000 times longer already than the error correction round. So these timescales are pretty problematic. So this is also, these kinds of exotic correlated errors are like a really important thing for us to keep working on just in the device physics before we even hit the QEC level. So we've put a lot of effort into making this really nice device. We've run the surface code that we're all very happy and familiar with. But the moment we were done with that, as you can imagine, we've got a stable full of experimentalists, and we'd handed them a lot of QEC circuits over the years, so we immediately got started running other things. And so now I'm going to tell you a bit more about two of our papers that came out very recently on experimental work on these two subjects. First, alternate versions of the surface code, because there are many ways to do a surface code. And then the second on the color code embedded on a square grid. So first, what do you mean by alternative? When I talk to theorists, now some of them have never considered anything past, well, of course, the experimentalist is capable of measuring a wait-for Pauli operator, aren't you? But sadly, we are not capable of doing that, so we have to build it out into actual gates. And that design problem is actually a really, I would say, difficult and interesting design problem. You can massively change the performance of your code by how you design the circuit. in this work, we sort of started thinking about this approach quite differently. Rather than starting with the surface code and simply deciding how to measure the operators, we started thinking, well, in general, how could you design a circuit to be sort of error correcting in the same way that the surface code is, without it just being the sort of standard construction? And we sat directly on this kind of concept of detecting regions, which are, I see that the slide deck has mangled the sentence, but let's, I don't know, sound it out together. A detector is a set of measurements with a predictable parity when you have no errors. So when you have an error, the parity will change and you can detect them. A detecting region is just all the places in the circuit where that detector would notice an error. It would be flipped by it. So these are like some very, very simple examples. Like this is a very simple circuit where this measurement is very predictable. And so if there's a bit flip error in the middle here, and this measurement is not the thing you think it is, you're pretty sure you knew what happened. So that's kind of a nice, easy case. You can see it can kind of get more and more complicated. This is a also very, very simple circuit, but at least at one place you're sensitive to Z and Y errors instead of only the errors that sort of anti-commute with Z. And you can start building up kind of more and more complicated detectors. Now, all of these are very trivial and would not really help you build an error correction code. But these are sort of what more normal-looking detecting regions look like. When you build out a circuit, you can end up with these nice little closed loops of detecting region that you can kind of imagine now. This is a nice shape, and it tessellates the plane. So that's kind of like a good thing to build a repetition code out of. And in 3 dimensions for a surface code, where you can tile 2 dimensions of space and time, that's what lets you build something that's sort of surface code-like. So yeah, now, instead of the task being pick your favorite code and then afterwards tell some experimentalist how to do it, the task to me is invent any circuit you like and then make sure it has detecting regions that tile the space-time of the circuit. And that pretty much turns into a good enough constraint with some extra things, like you'd like the detecting regions to be relatively local, not too high weight, and have a good kind of overlap with each other so you can build a good decoding graph. But this task actually gives you a lot more freedom than the kind of thing where you started off with a code with a really nice structure and then you only used one strategy to build a circuit out of it. So this is also a repetition code, although you can see that the circuit is much more jank. It's got weird stuff going on, but basically just by looking at the overlapping and tiling of these detecting regions, you can see what kind of code it is. And it turns out that this constraint, this is all you need in order to also have basically the same code performance. So these were 2 2D examples. Like I said, the surface code, you need to tile a sort of 3D volume of space-time. But it turns out that this is actually very easy to do, and so you can generate circuits that have very, very different characteristics, but still, basically speaking, implement the surface code and have exactly the same numerical performance as the surface code. And so these are 3 examples of specific weird circuits we found that have really nice characteristics for hardware. So first, the hexagonal circuit, where again, sort of surface code's made of squares. We've all been promised, like I've been promised since Austin Fowler 2012 that I needed 4 couplings per qubit to make a square. Seems good. Turns out, completely wrong. You only need 3. You can compile the surface code down to a 2-round cycle that only uses 3 couplings per qubit. So it's actually, the qubits are on this white grid, and they're in a hex grid. And nonetheless, you implement the square surface code over the top of them. So this one turns out to have, like I said, exactly the same performance as the surface code because it is implementing the surface code. It's just implementing it very weirdly. So another one we can do is implement the surface code, this time on a square grid, but we use a kind of circuit trick in order to move the patch diagonally on which qubits it's supported on. So you can see specifically here, right, like this qubit was a measure qubit. It was used for syndrome extraction. But at the end of this round, it's actually started being a data qubit, and it's not being used for syndrome extraction anymore. So this kind of seems just like a cool parlor trick. Like, yes, I can make the surface code kind of jiggle sideways. But because, if you remember when we were talking about leakage, removing leakage from a qubit is very easy right after it's been measured and kind of difficult, developed technology otherwise. Because we can switch which qubits are measured and which ones aren't, we can make sure that every qubit has an easy leakage removal every second round. And this means that instead of using that DQLR strategy I mentioned before, we can kind of just run this circuit backwards and forwards and make sure that the leakage never really gets to live that long, because every second round it's going to crash into something that removes it. So that turns out to be a kind of fun circuit equivalent. And the last one that's kind of the most complicated is you guys really bullied us as experimentalists into doing CNOT gates. We never really wanted to. The natural gate for 2 transmons capacitively coupled is a thing called an iSwap. It is a gate that we all used, like back in when I first joined Google when we were doing the supremacy experiment, that experiment was on exclusively in ISWAPs because the QEC theorists hadn't told us we couldn't. So actually, it turns out, again, if you manipulate the circuit kind of drastically, you can compile the surface code down to something that handles, that works fine in ISWAP gates. Now, previously, it was considered that this was not really kosher, basically because of the swap bit of the ISWAP. An ISWAP is basically a CNOT gate and also a swap. Now, the CNOT provides the entanglement. That's great. That's what we always wanted. But the swap made it very hard because it sort of tore the stabilizers apart. Like you can kind of imagine if you started off as a square, after one round, you would end up with one of these nasty pointy shapes. And if you kept going, the shape would get pointier and pointier, and you would need more and more gates in order to measure the stabilizer. It turns out in the circuit picture that it's not that hard to find a circuit that, while it tears up the stabilizers a little bit, it sort of untears them and then shoves them in the opposite direction in the next cycle. And so you're always sort of oscillating back and forth between these kinds of variously disturbed lattices, but you never really wander all the way off. Like you don't keep tearing them, so they don't keep getting worse. And this lets you compile the surface code for something with a swap component. And now all of these I've said for the surface code, but these are all very generic tricks. Like any wait for code that you can think of has an equivalent of a period 2 hex lattice construction. All of the codes that I've looked at so far that are planar have a walking construction. And ISWAP gates, like I said, are sort of very common. And later there are constructions for things like color codes using ISWAPs as well. But of course, like I said, I'm an experimentalist. The most exciting thing for me is just running the thing. So here is this paper, very recent, just from last year. Oh, start of this year, I guess, is when it finally went up, where we have each one of those 3 codes I just mentioned, and now we've run it on the same device. Now, actually, sort of by accident, this is on a different device than the previous paper. It's not exactly the same one, so you shouldn't compare the numbers directly. But on this particular device, the performance of the hexagonal surface code circuit actually exceeded the performance of the standard square one. And that basically boiled down to the fact that we only had to calibrate 3 of the gates per qubit instead of all 4 of them. And that gave us additional optimization freedom to make those gates better. And so actually, this code outperformed the standard one. We also implemented the walking code. Here I'm going to explicitly point out all 3 of these are in this sort of beyond 1.5 lambda regime. So they're in the case where they're going to descend forever. But you can see there's overhead. Like these do not perform quite as well as the standard codes do. And that's because they're sort of demanding kind of different things that we haven't optimized our device for. So the walking code requires you to measure out both sets of qubits instead of just always measuring out one set of qubits. So the readout calibrations become significantly more difficult. And then the ISWAP gate, of course, is using a completely different 2-qubit gate. Here we just pushed ahead. This device was really optimized physically for the CZ gates that we're used to using. It's not impossible to do an ISWAP gate, but you can see that they were a little bit more difficult to pull off. But yeah, it was really impressive to see that all 3 of these alternate circuits were below threshold on a device that was not optimized for them physically. But the last thing I'll say is also calibration and optimization is really hard. When you do 3 circuits, you genuinely have 3 times the amount of work. And not all of the problem with these codes being a little worse performing is actually anything to do with the code circuit itself. I'll show you some quick examples. So like here you can see this is the standard code that we actually ran on exactly the same device. So this is like a kind of fair comparison. And like I said, the hex code actually did a little better because we managed to improve the 2-qubit error rates with that additional optimization freedom. But like, for example, the ISWAP one performed quite a bit worse. So we were sort of only just in the 1.5 lambda regime. But while there were some kind of special problems, like now we have this new issue unique to the ISWAP gate on this device that has a sort of C-phase entangling error. The substantial fraction of the error budget is actually the fact that in this calibration set, when we were operating that device that week, we had really, really bad idle errors. The dynamical decoupling during readout was not performing very well. Sadly, we have a finite amount of head count and bandwidth and time on fridge. So this was not something we managed to sort of fix before we wanted to chuck this paper out. But if you want to think ahead as to the sort of relative usefulness of these codes, this is not the right ratio to worry about. Genuinely, I would think that the device details, things like, oh, the dynamical decoupling is sort of hard to optimize on this device, are sort of more dominant on determining performance than the actual which one of these codes you select. So at least from my perspective, this is like an excellent kind of proof of concept that if you designed a device specifically around one of these codes, it would perform as good, if not better, because these kinds of advantages are really advantages for the hardware engineers, and we're not even exploiting those yet. Yeah, and then last, I want to say that basically using the same detecting region picture to design a good circuit embedding, we can also run the color code, which is sort of very related to the surface code, so maybe this shouldn't be too surprising. But we can run the color code on our nice square grid. This uses more, it uses 2 measure qubits per plaquette, but we get out both of the stabilizer checks and the color code at the same time. You can see that we've done a number of weird distortions to the code. You probably would not normally lay it out like this. And the reason is because on our device, readout lines, like the qubits that are multiplexed together and have one readout structure across many qubits, they're arranged sort of diagonally on our grid. So we wanted to try and push the measure qubits to be aligned with that diagonal. So instead of having nice kind of hexagonal plaquettes, we should have shoved them around to make the device performance a little better. And yeah, this one also performed below threshold. Again, sort of like only just beyond the 1.5 that I think everyone should take as the real proof of useful error correction. But also in the same paper, the color code has an extremely nice characteristic that the single qubit Cliffords are transversal. So you can just kind of do them. So we did, this is very close to experimentalist heart, doing interleaf randomized benchmarking to see whether your gate is any good. And indeed, the transversal logical Cliffords come out to be not too bad. Also in the same paper, we did magic state injection, where you can take a small color code, you can basically inject an arbitrary state sort of non-fault tolerantly. This is sort of like the starting point for then going towards magic state distillation in order to finally do kind of real universal quantum computing. And then also in the same paper, we did lattice surgery between 2 small color codes. And so again, this is sort of like once you have spent the years developing the very, very nice device that you convince the graphical artist to make you a nice slide for, it tends to work on almost everything if you do it right. So yeah, this is really saying that we kind of spent a lot of time focusing on making the device itself good without over-optimizing for even one task, without over-optimizing for our favorite wait for square surface code. Once you have the low enough error rates, you guys can go nuts. So I don't know, suggest a circuit if you like one. And then the last thing I'll say is you kind of imagine, we're not going to stop here. These 2 experiments that I've kind of explained to you now both have very natural extensions that we're going to be starting to do next. First, these adaptive circuit code circuits, especially the hexagonal one, sort of tell you that you've probably overdone it in terms of resource estimates. If you only need 75% of your couplers, if you build a square grid and one of your couplers is dead, obviously that is not a big problem. And so this paper, finally a theory paper for the theory workshop, where we've looked at a circuit construction technique that applies the same kind of circuit flexibility to dead qubits and couplers in various patterns. And it builds period 2 and, in general, period 4 circuits that have really, really nice characteristics for scaling when you have really high densities of dead components. And so this is the kind of thing that, again, you get to go to the hardware engineers and say, I know you did an awful lot of work making all of the qubits work at the same time. Would you like to have 1% of them just not work? And the fabrication engineers are very, very happy with this suggestion. And then in a more QEC performance direction, the color code, and especially this kind of circuit for the color code, is one of the sort of load-bearing elements of this new theory work by Craig Gibney, which is a different way of producing very high accuracy magic states. It really exploits this characteristic of the color code that you have these transversal gates, and it kind of repeatedly checks a magic state over time. And then you can see that, so down here we have a color code, and then you sort of have to inject it into a really large surface code in order to be compatible with the rest of our plan, at least for now. Although I will say if the color code keeps performing, who knows? Even Austin Fowler could be surprised. So yeah, these, we have no shortage of new experiments to do. These are very natural extensions of the experiments we've just done. But we also have a whole bunch of other things up our sleeve, stability experiments, as I mentioned before, lattice surgery. So yeah, I think it's a really exciting time for us here. And hopefully, I'm exciting you as well. Like I said, if you have any suggestions for fun things to do and for fun codes you might be able to embed on a square grid, come and talk to me. And so that, yeah, thanks very much. Obviously, I want to thank the entire Google Quantum team, which is, as always, rapidly growing. And also shout out that we're hiring at the moment. Our intern hiring is on for the next couple of months. So if that interests you, come and talk to me. Thanks very much.
Thanks for a great talk, Matt, and thanks for competing against the football. Well done. We've got some time for questions, so let's start with Andrew.
Yeah.
Thanks very much. That was really great. So I just had a question about the high energy events.
Yes.
So I was just wondering how were you attributing those to gamma rays as opposed to neurons?
Ah, yes.
Also, could you just sort of comment on the sense that I get in the literature, and maybe it's not right, that not all groups are seeing these high energy events at kind of the same rate?
Yes. Yes, so both of those things are true. Sorry, I should say the second thing is true and the first thing is interesting. I don't have a slide because it was mostly work not done by our group. But there was sort of like a substantial academic collaboration. Even before I started, I did my PhD working on the kind of impact events, so I have a long history with it. But even before we started working on it at Google, people had already seen these kinds of events in some devices, but also not seen them in other devices. And it was really sort of not obvious what was going on, what the physics was, but it was obvious it was going to be a problem. Since then, we've discovered a whole bunch of things. So first, I can say that people have done really fantastic metrology experiments, including two that I can really think of, one from MIT and one from China, I forget, I think Shenzhen, but I can't remember, where they put genuine astronomical detectors around their fridge and found the relative contributions of the gamma rays and other things like cosmic rays. So we do know the relative rates, we know the energy depositions of these things. Broadly speaking, we surprised 0 people in the detector community when we found this problem and when we started describing this problem. So like, as a good example, years before those experiments were run proving that the issue in qubits was this issue, I was promised that it was by pretty much everyone who made telescope detectors that I talked to. And they correctly told me what the relative rates were. They correctly told me what the energy depositions were going to be. So we're not really, we're really reinventing the wheel here. The second thing is, there was also this mystery that some groups kind of saw it and other groups didn't. For the most part, almost everyone who was making low gap qubits, like out of things like aluminum, was seeing it, with only a couple of exceptions. And most people making really high gap qubits, like out of niobium, were not seeing it. I mean, that's because if you use a really high gap material, you tend to accidentally gap engineer your qubit well. And if you use a low gap material, you tend not to accidentally gap engineer your qubit well. So this turned out to be like a massive difference in sensitivity for this kind of thing. Since then, I think we've closed the loop. Like Ted Thorbeck from IBM has pretty much, at this point, I think, confirmed that in their devices, if you look really, really hard, you can see the signature of a gap-protected impact event. And in our devices, now that we're gap-protected, those two things look very similar. It's just much harder to find if you're not looking for it if you're gap-protected, which some groups were and some groups weren't. Another effect was that plenty of groups were putting down material that ended up absorbing a lot of the phonons, which makes the event 10 to 100 times smaller. And this also makes it harder to find. But yeah, broadly speaking now, I think that all of the experimentalists are pretty much in agreement about the rates of this happening and what makes it more or less dangerous for your device. Although, yeah, I will say the gap engineering was sort of maybe the biggest ingredient in this because it really turns the effect really on or quite a bit off. You can get 6 orders of magnitude protection if you make the gap engineering 2 times the qubit frequency. So that's a neat trick that only some of us were using by accident. Yeah, Catherine? Yeah.
You mentioned that you had these time-like correlated errors on single qubits that you haven't understood the physical mechanism
Yes.
behind yet. Are you planning, are you going to mitigate that with decoding or with these alternative circuits, or are you going to try to understand the physical mechanism behind that and engineer around it?
Good question. I'm biased. I'm an experimentalist. I want this to go away. I want a physics solution. Actually, same as with the cosmic rays. People in our group are working on things like, can we convince the decoder to handle this and how? And there are good solutions there as well. I think the best solution is always doing it in the device. But there's no reason not to do it in both places. Like you saw also with the impact events, even if you make a really massive physical improvement, it doesn't tend to completely remove the problem. There's always kind of a further issue. So I think that working on for example, kind of correlated decoding or being able to adapt the circuit you're doing, a really good thing you could do here is the second you notice this is a problem, instead of just having it, you could treat this qubit as dead for the next several milliseconds and then monitor it to see if it's alive or not. And just not use it for the surface code. So improving things like our circuits for dead components to make that cost lower, improving things like our decoder's ability to figure out that something might be going kind of badly and adapting the circuit during the error correction experiment itself. And then, yeah, the decoder just being better at handling these things. So in this tail where the density is a little lower, we can put it back in and know that it'll be OK. All of these things are going to be kind of important improvements. But yeah, deeply it annoys me to see this, so I want a physics solution. Oh, yeah? Oh.
Yeah, I was kind of interested in your very first matplotlib color cycle plot.
Oh, yeah?
Very start.
Sorry, which one?
The one that you had the matplotlib colors for.
Oh, yeah.
Yeah, I was just kind of curious what exactly goes into that simulation.
Oh, yeah. It was, again, as you might guess, it wasn't the most sophisticated. What we're doing here actually is, and I didn't mention this, but this pink one is basically we've measured the component errors in our actual device for the distance 357 experiment, and we've put that into a Pauli error model. So it doesn't include everything that you might want it to include, which is why the lambda is a little better than it should be. This is better than reality. But then after that, so effectively you can think of this as sort of not reflecting reality, but a kind of close Pauli independent error model tuned to be vaguely in the right ballpark. And then after that, we scaled this alpha, which just multiplies all the errors in the independent error model by that factor. And then after that, we benchmark a lot, all the way out to really ridiculous distances. And so, like I said, this skips over loads of actual device details. It doesn't have nasty correlated errors in it. But just in terms of an independent error model, after that, you can just fit the lambda 3.5, which is just the first 2 points, and then you can just look at the rest of the points. So this is sort of vague numerical guidance, not publication approved, really, really shiny figure 1 stuff. But I think it gives you really, really the right idea, which is that this bendy stuff is not a lie. It's very much a true underlying fact. It's not due to weird device details like correlated errors. It's really an intrinsic part of how these circuits work.
And is there, will all of those curves eventually flatten out at some point, or is there actually some point where?
They will flatten out to somewhere, but they won't all flatten out. OK, yeah, I need to be careful what I mean by flatten out. These top ones tend to go back up. This green one looks really flat, but actually out at very, very large distance, it probably tends back up again. It's only these ones that are basically straight that I would trust to any substantial distance, if that makes sense.
So is there actually some cutoff where you can say below this, they would never?
No. The thing I would say to be more strict is the reason we're playing this entire game is because we're talking about this kind of silly concept. Lambda is an exponential fit, and I have subtexted it with 2 very small numbers. It's not an exponential fit. It's not even kind of a real thing. We're stuck measuring this because we only have distance 3, 5, and 7 codes. But in the end, we want big distance codes. And you can see that you don't have to worry about the small size effects when you're all the way over here. So really what I would say is the real TLDR of this plot is just don't really trust the small stuff. Really what you want, the way you really want to see a lambda is having big codes and seeing that you get a lot of lines in a straight line on an exponential plot.
Thanks for your interesting talk. I'm wondering about the neural network.
Oh, yes.
Doesn't it be trained for each code distance individually, or are there any methods, are there any machine learning techniques for scaling up this?
Yeah, so it is not trained for each of the distances. It is trained on our largest thing. Actually, well, OK, so the neural network is trained in 2 broad steps. First, it's trained entirely on synthetic data, including up to very high distances. This effectively, and actually it's similar caveats to things I said before, it includes some kinds of hardware-inspired errors, but it is not experimental data, so it doesn't include nasty correlations we don't understand yet. So we put a bit of work into making better and better synthetic data, but it's not reflective of reality. But that's what the vast majority of it is trained on. And that's trained up to really high distances, as I said. And then kind of right before we really run it on the actual experiment, we fine-tune it, which is a pretty typical maneuver in machine learning, I would say. We fine-tune it on actual experimental data on our biggest distance, basically. And that really improves the performance quite a bit. Because at that point, broadly I've had this explained to me as, during the first thing, it's learning the actual problem and what to do about it. But during the fine-tuning, it's learning all the things actually wrong with our device. And this makes it quite good at decoding that device. You do have to do the fine-tuning differently on different devices. we don't do the fine-tuning differently for different runs of the code, different sizes, and we don't tend to change it over the several months we're using a given device, but you can. So the fine-tuning is important, but it also has diminishing returns. You could imagine fine-tuning it every 10 minutes, but this would be a horrendous waste of time. So this one is trained on synthetic data and then fine-tuned on the largest distance.
You spoke about the detectors of these weird subcode things as being like tilings of like 3D.
Yes.
Like it's not 3D space, right? Have you ever looked at one in 3D space?
Yes. It won't surprise any of you who've seen Crumble or know who Craig Gidney is that we have very bad, like really janky visualization tools for this kind of thing. They're good fun, but honestly, it's a very difficult UX problem. Seeing these kinds of things in 3D, there's just kind of like too much information all over the top of each other. I tend to find it kind of helpful to plot one of them at a time in space-time. And that is kind of an object that you can look at and rotate. And it's also actually an object that we've 3D printed a bunch of and have in the office, which is kind of fun. Honestly, the best tools we have for it probably are still Crumble, though, like the 2.5D-ish look, where you're like moving through time or space, tends to be kind of, I think, more helpful for humans to interact with than the genuine 3D one. That said, Craig owns one of those Valve Index 3D headset things, and he really enjoys looking at them. So.
But how does this 3D printed thing look like?
Oh, I mean, honestly, the best thing I can say, if you want to know exactly what it looks like, is look at the Psi Quantum paper with the Pauli webs, because they've pretty much made a nice diagram. It looks like that thing, because that's what it is. Like,
It's like one of the crystal structures.
yeah.
Can I follow up very quickly on that question? Because these tessellations are very nice when you have these mirrors able to right? What happens? Have you ever thought about using sort of detecting regions to do cross circuits for the ones that are the good LVPC codes where you have a little bit of long distance things?
Yes, it tends to have less of a geometric intuition at that point, especially for me. But Craig and I had a good fun time at one point trying to look at, like, can we geometrically reinterpret, for example, IBM's code. And you can make a lot of progress that way. I think you're always kind of, it's like, the visualization, especially in 3D, gets much, much worse when you have these long distance things. So I'm not sure the intuition is quite as convenient. So at least for now, I'm leaving the LDPC codes to the theorists. But
It will work. I know it was not going to work, but we'll discuss.
Oh, good, yeah.
One last question, yes.
In the managed state cultivation,
Yeah.
at the end you have this kind of warping of the lattice.
Oh, yeah.
Is that something that you can deal with in the same way that you can deal with the color code using these new techniques?
Yes. Actually, you can see that there are like a whole bunch of, I wish I could zoom in, fun details here. Like here, actually, Craig has used the standard hexagonal circuit for the color code instead of this like chevron-y one. But you can also see that he's got these kind of weird extra bits at the side where the color code interfaces with the surface code. All of those are also just, in some sense, these circuit details that you can sort of manipulate. In reality, we would probably replace this middle bit with this thing, and that makes this thing a little more complicated. Craig was getting to the level where he wanted the circuit to be valid so we could benchmark it with hardware errors, but he didn't keep some of the really device-specific constraints, like us building our readout lines in diagonal lines is just because we do, not because we have to. So Craig said, I'm going to tell you not to, and that's fine. That makes nice patterns. You could just as easily perform those manipulations inside the grafted surface code like that, and it would be OK.
Okay, let's thank Matt again for a great talk.
Well, thanks very much.
We've got morning tea over there. I'm going to see if